team. Now, now choosing. So now we have come across the what are the different parameters in the lightning arrestor. So now let's talk. What are the chances of occurrence of these surges? Team? What are the chances of occurrence of these surges? One is the occurrence of surges on due to the traveling wave process. Traveling wave process. Second one due to the inductive voltage drop. Inductive voltage drop. And other things by discharge currents. So some other things, but mostly these things. So now let's assume team, I am having a lightning arrestor. I am having the lightning arrestor, which is connected to the face to the ground. And now this is my transformer. This transformer insulation is protecting by this lightning arrestor. On this lightning arrestor, the protective level is the U max. The protective level voltage is maximum 823 kV. 823 kV. See, generally, how the lightning falls on the system? Generally, the lightning will fall directly on the transmission line. So if the directly lightning falls on the transmission line, if I am placing the lightning arrestor here, it will fail. So lightning arrestor will discharge the lightning impulse only small content. The greater, the bigger content of the lightning impulse will be discharged through the flashovers of the in the insulators, or maybe it will hit onto the shield wire and it will directly enter into the ground. So lightning arrestor will face these surges maybe due to the back feeding of my fault from the ground to the black flashover, in the sense flashover, or maybe a sudden rejection of loads, these kinds. So much magnitude is not appeared on the lightning arrestor. If the lightning fall near to the lightning arrestor, definitely lightning arrestor will fail. It's not able to handle that. So that's the reason in the high voltages and extra high voltages, we will lay again a shield wire on top of the transmission lines, because some part of that it's entered in the grounding. And if anything, if any more extent of this magnitude is available, that when it is coming from the ground, returning to that again alive as a black flashover action, if it happens, then the lightning arrestor comes into the play. So now let's assume the protection level of my lightning arrestor is 823, as we discussed about these characteristics. Now a surge appeared here. A surge was appeared. Suppose the distance between these two one is let's assume 30 meters. I placed it 30 meters away the lightning arrestor. Now this is a surge, lightning surge appeared on here in the between this. So the surge steepness is, suppose it is occurred maybe on the line, it is traveled. So it is traveling here. So the surge steepness is 1000 kilovolts per microsecond thing, per microsecond. Generally, what is the velocity of the propagation of the light? 300 millimeters per second, right? So if I am considering that here into this velocity of the propagation traveling length concepts, then this lightning arrestor with this 30 meters, if you see here, only nearly 100 kV of the lightning arrestor, 100 kV of the voltage will be seen by this lightning arrestor. 100 kV is not at all a matter for my lightning arrestor, because it is continuously operating at 360 kV. So this 100 kV, it will travel to this like this, and when it's reaching to the transformer, the impedance of the transformer is different compared to this. So there will be a reflection of this one. So when it's coming back, and now it is adding to my normal magnitude. So now the lightning arrestor seeing the voltage is not 100 kV, now 200 kV. and similarly 400 kV, 800 kV. So up to some extent, my lightning arrestor is if it's seeing at 400, 800 kV, so it will discharge the discharge of the current. So this is maybe due to the surge happening due to the traveling line process, and maybe due to the inductive voltage drop. So we know that voltage U equal to L into di by dt, right? Current. So L, suppose let's assume the inductance of the line is offered by line is 10 microhenries into suppose a lightning impulse current of 10 kiloamps per microsecond was fall in the system. Then if you see again, it sees only 100 kV. So for 100 kV, the lightning arrestor will generally not will not work. So these are the general ways of occurrence of the lightning surges. And again, the protection of the protection of the lightning arrestor means the residual voltage at nominal discharge current. Suppose my at 823 kV, my lightning arrestor is discharging a current of 10 kiloamps. When a 10 kiloamps is discharging through this lightning arrestor, entering into the ground, so some voltage will develop, that is a residual voltage. So that is generally, as I said again, nearly to the 1.4 factor. Generally, we have to maintain that is between the standard BIL level of my transformer to the lightning protection of this. So that is nothing but, so this 823 kV is appeared here by 10K passing through this. So this 823 kV should be 1.4 times, then it is equal to the standard BIL level of my lightning arrestor into divide by 1.15 as a factor of non-self restoring insulation. So that is the point. So this 823 is nothing but a maximum residual voltage that appearing by the discharge current of 10 kiloamps. So my lightning arrestor. So now we have to check when you are sizing the lightning arrestor, we have to check some conditions, like one is the rated voltage of the lightning arrestor, the maximum continuous operating voltage of the lightning arrestor, and also the protective level of my lightning arrestor. These are the three important things we need to consider. To know about again the protection, so you can do the continuous over voltages, maximum continuous over voltages, as we see in the formula before. Again, we will see. We will go to that, and you can also come to know that how to calculate the rated voltage. I will show you that. But to know about the protective level of my lightning voltage, again, it depends upon the lightning arrestor selection. Lightning arrestor selection in the sense, how much discharge current you are selecting through that lightning arrestor, whether 5K, 10K or 20K, and other thing, the line discharge class of the lightning arrestor. Again, what do you mean by line discharge class of the lightning arrestor? It is in the market, we can find the classes of lightning arrestor: class 1, class 2, class 3, class 4, class 5. These classes will tells us what is the energy absorbed, what is the absorption capability of the lightning arrestor when it passing the 10 kiloamps of the current through it. In a simple way, let's assume when you are choosing the lightning arrestor always two conditions to be checked. One is, what is the distance between the arrestor and the device to be protected? Other one is the over voltage stresses in the system. These two generally we will get from the insulation coordination study. So lightning arrestors, as we discussed it so far, we are checking the stable continuous operating voltage, like by checking the continuous MCOV, maximum continuous operating voltage, and the rated voltage. And also we talked about the protection level of my lightning arrestor with some factor of 1.4 that. In addition to this, one more important factor which will influence again on these two parameters is energy absorption capability of my lightning arrestor. The energy absorption capabilities, see, instantaneously when a fault occurred, when a 823 kilovolt of voltage appeared in the system, that energy instantaneously some energy is appeared on this on your lightning arrestor during a single discharge, not allowed to exceed a value. Sorry, not to exceed a value of metal oxide resistor thermomechanical overstress limits. I mean that in a simple way, when you are discharging this 10 kilo amps of current from my lightning arrestor, a single discharge, the energy which is accumulating there, that should not exceed a value of my metal oxide resistor, which is inside my lightning arrestor. That which should not exceed a value of metal oxide thermomechanical overstressor limits. Thermomechanical overstressor limits. So that will termed as a single impulse energy absorption capability of my lightning arrestor. In a simple, suppose I am sending a 10 kilo amps of current through this lightning arrestor. So the lightning arrestor is again inside the lightning arrestor. You can see a metal oxide resistor blocks, which are in the shape of this metal oxide resistors. Metal oxide resistors. This metal oxide resistors having this is nothing but ZNO blocks, zinc oxide blocks. These ZNO blocks having a characteristic of this nonlinear characteristics. So when 10 kiloamps of current is passing through this, so instantaneously when a single discharge of current is flowing through this, obviously a energy will be accumulated over there. That should not exceed the value of my metal oxide resistor thermomechanical overstress limits. So that value we will call as a single impulse energy absorption capability of my lightning arrestor. Then because you are doing single discharge through that, during the single discharge I'm talking, so it's a single impulse energy absorption capability of my lightning arrestor. Means when energy injection, even though the energy injecting through that lightning arrestor is only few microseconds to the milliseconds, even though it is only for microseconds to the milliseconds, but due to the instantaneous nature of impulse, like in a highway, so the temperature will be rising soon. Due to this temperature rise, the excessive tensile and comprehensive forces will act on that metal oxide resistors, ceramic, which will lead to the cracks on my resistors. The resistivity property will fail, so lightning arrestor will damage. ZNO blocks will fail. ZNO blocks are failing due to the temperature rise. Why this temperature is rising? Due to the discharge of the current through that in a single shot. So to know this, we have to also size the metal oxide resistors. They are having different sizes, like 40 mm diameter with 50 mm diameter, 60 mm diameter. So we are having a wide range of metal oxide resistors in terms of the diameter. So we have to select that. It's nearly to 20 mm to 45 mm, nearly wide ranges are there. So we have to select based on the energy absorption capability of my lightning arrestor. In a simple way, if you check the thermal energy absorption capability of my lightning arrestor, Let's see. We are obviously it is current is passing means so electrical power losses will be there. So let's assume this is my electrical power losses of my system. So electrical power losses. This electrical power losses giving the temperature. This is the temperature. Due to this electrical power losses, the heat is developing. So that curve is like this. That curve is like this. So it is having two here. So this is the stable operating point. So this is the stable operating point where the thermal balancing equation prevails. Means whatever the energy up to this part, whatever the energy it is releasing, it is cooling down by the lightning arrestor as a principle of convention, what it may be. Apart from this, the thermal stability, this is the thermal stability limit. This is the thermal stability limit, which is typically has a value between 170 degrees to 200 degrees Celsius. So apart from this, no cooling process. Cooling is not possible here. The metal oxide resistors will be burn out, means will be loose. So whatever the energy you are passing through that, so the each metal oxide resistor is facing that energy, and those should be capable to handle that energy. So that is also one more factor we have to consider when you are selecting the or sizing the lightning resistor. So this, how can we know? That is the manufacturer dependent. So how can you know? How can you know this? So for this, we are talking with a term called line discharge class. So this energy capability of my lightning resistor, we are talking with a concept of line discharge class. Line discharge class. And what is the current? Nominal discharge current. How much current that has to flow inside the thing. So these two will gives the exact size of my means exact rating of my lightning arrestor. In a simple way, the nominal discharge current we have to select. So this nominal discharge current and the line discharge classes to be selected by the lightning arrestor depending on the some factors. Let me see that. So from this, we will conclude the this is the size of the lightning arrestor I required for my application. Any doubts, team, till now? Clear? Fine. In a simple way. Okay, great. So in a simple way, to understand this better, let's do some example, team. So as I said, the metal oxide resistors are in the range of 20 millimeters diameter to 45 millimeter diameter, right? Right. Generally, the residual voltage, as per the guidelines, the residual voltage, again, the residual voltage means due to the passes of 10 kiloamps, residual voltage per millimeter of height during 10K discharge, during the 10K discharge is nearly residual voltage per mm of height, means of height of this metal oxide during the 10K will gives you the 10K residual voltage. Means I mean, suppose if I'm selecting 45 mm, so 45 into 10, so it's nearly to 450 volts per millimeter per lightning arrestors, and we generally be having a 280 volts per millimeter per 420 kV system. For 20 kV system, 280 volts per millimeter is my residual voltage. residual voltage per millimeter for 420 kV lightning arrestor with a dia of 70 mm, with a dia of 70 mm metal oxide. Now, in the 400 kV, let's assume we are having 45. Suppose if I'm taking the 45 mm high lightning arrestor, so 45 into 280 volts, right? Each can withstand a voltage of 280 volts. 280, which gives you 12.5 kV. Near to, like 400, so that's 12.5 kV. Now, in order to, so what is our again, in order to achieve the lightning protection level, which is 823 kV, how I got 823 kV? By dividing it with 1213 by nearly to 1.4 or 1.5 times, I got this. So how I got 12.1239? The BIL level, which is 1425 into 1.15. And how I got 1425? This we will get from the insulation coordination study that we will see in our next classes. So this is the phenomena. So to maintain this, to get this lightning impulse protection level of my lightning arrestor, so if I'm dividing this with by 12.5, so it results to 66, 65. So 66 number of these this 45 mm, 70 mm dia metal oxide blocks are required for 420 kV system. So 66 kV, each ZNO block inside the lightning arrestor, lightning arrestor can have a capability of energy absorption capability is 3 kilovolt per joules. 3 each one is 3 kilovolt. So again 66 into 3, how much it's coming? 6 is 18, 18, 19. So 198 kV, the standard one. So 66 number of arrestors, this ZNO blocks are required for with a because this is a 3 kV. Now for 70 mm dia, what is the one? Each one is 70 mm dia. So 70 into 280, which is coming to 5, 6, 14, 21. So each leads to 2.1 kV, maybe 2.1 kV, maybe. So I require 66 number of ZNO blocks. This can be placed with 2 number of stacks or 3 number of stacks, whatever maybe. This is how the lightning arrestor will be there. For example, in a simple, what just again repeating you, the residual voltage is the voltage. So I am selecting the ZNO, this diameter of my metal oxide. So suppose if I am selecting 70 mm dia of my lightning metal oxide, this block, then it is having a capability of, it can 280 volts per mm. So 280 volts per mm, but my required one is 823. So 280 volts per mm, 280 into how many, what is the, I am considering 45 mm, right? 45 mm lightning resistor, high resistor, I am considering in the here. So 45 into 280 gives my 12.5. So 12.5 when I am dividing, I am giving, I required 66 number of 45 mm ZNO blocks to attain 823 kV of protection level. A simple example over this. So removing all these things, let's do the calculation, then you will get an idea. First of all, let's assume my continuous current. This is, suppose if it is a 220 kV system, 220 kV system. So 220 kV divided by root 3 into root 2 will use my UC into have a 1.05 as a continuous as per IEEE conditions 0.1 for the harmonics content. So this will give my continuous operating voltage of my this lightning arrestor, continuous operating voltage of my lightning arrestor. And this continuous operating voltage again depends upon my at the fault condition stream. We are having two types of earthing. One is solidly earthed, other one is isolated or resonant earthed. In solidly earthed, this is the condition. The continuous voltage should be greater than or equal to 1.05, means 5% tolerance into US, which is uh, the system voltage by root 3. And come to this resonant or isolated grounded system, this UC should be greater than only US, because here the rated these are generally decisive for continuous operating voltage. Generally, we will consider the system voltage as for the resonant or this one. And for the rated voltage, to calculate the rated voltage, we are considering the factor of 1.25 to this UC will use my rated voltage. And here also same, the greater than 1.25 times of the US system voltage or UC, whatever it may be. And this 1.25, it's there is no physical reason how we got 1.25. It is a manufacturer logic. Means to attain these values, generally this rated voltage is falling under at a range of 1.25 times of its continuous current. So it was purely empirical resulting. So the rated voltage can also be examined by completely different approach. This is the one way of approach. Other one is by examining the temporary over voltage state. Generally, for solidly earthed systems, temporary over voltages nearly up to 1.4 times by considering that fault factor of 1.4. That will be stay in the system from few tens of seconds to up to a several seconds. So the power frequency voltage above its continuous operating voltage can only be applied to the lightning arrestor for a limited period of higher voltage, shorter the permissible time. We know that. So power frequency voltage versus time UT characteristics will be there. So that will use us the wave factor, which is K suffix TOV. You can see this in the lightning arrestor characteristics where data sheets K suffix TOV. So this is the ratio, which is ratio of permissible power frequency withstand power frequency voltage and RMS rated voltage. RMS rated voltage. This is the K2UV. So this we will see from the grafting. See how much time the temporary over voltages you are asking to means will be there in the system. So based on that, the KTOV will be there. So that is also one more factor to size this to calculate this rated current. Means rated current can also be calculated with the rated current divided by UTOV by KTOV. UTOV is the 1 second voltage which occurs in the system for a time period of 1 second. So you can calculate this. Generally, this KTOV will be 1.15 times T. So whatever the maximum is, this is the maximum, this is the maximum. The maximum of both this UR1, UR2 by doing the two studies. So that we will consider as a rated voltage of my lightning arrestor. Then again, I am repeating that when the rated voltage is finalized, again, I am dividing that with again 1.25. Then I will get the actual again my continuous operating voltage. This is again a back way of doing. So this is how I am calculating the continuous operating voltage and rated voltage of my lightning arrestor team. I will show you with an example. So the continuous operating voltage is generally a system voltage into 5% tolerance. And come to the rated voltage. Rated voltage can be done in two ways. One is just by taking 25%, 1.25 times of the continuous voltage. Otherwise, taking a KTOV factor, which is ratio of power frequency voltage to the rated voltage. So we are having a graph. So from that graph, we can see if my temporary voltages are existing for some 10 seconds, then what is the factor of KTOV? That we will there. So again, we are multiplying this with my rated voltage. That will gives you the rated voltage. Sorry, UR2. So what is the maximum of UR1 or UR2? That I will consider as my final rated voltage. And again, I am dividing that with my 1.25. So I will come to note that what is the UC. Maybe the first the derived UC will be same, result same, or it will be high. So that is the calculation of my continuous operating voltage and the rated voltage of my lightning arrestor. And the next one is selection of discharge current team. So in a arrestor, generally we are having a discharge currents of 5 kiloamps, 10 kiloamps, 20 kiloamps in the market. Mostly it is recommended, all recommended is 20 kiloamps and 10 kiloamps and 20 kiloamps stream. Because it's totally depends upon the size of the MBO block, as we discussed it before, MBO metal oxide dia. So based on that, let's suppose in a simple way, if you ask me, if I am having a 5K, if I am selecting a 5K lightning arrestor, if I am testing the operating procedure or if operating principle of this, then the high current impulse of 65 kA we are applying 2 times, and 20 times of the basic lightning impulse of 5 kA we will do, and we will check whether it is it stand or not. Similarly, for 10 kA it will be more. So it is recommended that generally all the cases it is recommended to have a discharge current of 10 kA. And if you see above 400 kV or 400 kV systems, better to have a discharge current of 20 kA. So based on this, now the line discharge class will be selected. Line discharge class will be selected. So line discharge class, again, as I discussed before, the line discharge class can also be assumed or presumed in a way that the long transmission line charged to a certain over voltage will discharge through connect this arrestor in the form of transmission line, traveling line process, as we discussed it before. In the line discharge classes, generally it was said that less than 245 kV system, one, we are having 5 classes of line discharge. For less than 245 kV, 1, less than 300, 2, less than 420 kV, 3, less than 550, less than 850, we are having different classes. And this line discharge classes also be categorized with the MO blocks, metal oxide blocks. If it is having a 50 meter dia, it comes to the line discharge class 1, means energy absorption capability team again here. And come to the second 50 or 60 class 2 60 70 70 80 above 100 dia, it is comes to the class 5 lightning arrestor. Class 5 lightning arrestor. So by this you are selecting the lightning arrestor. So now I will show you how this will be a factor of our case. Let's assume, let's go to a calculation. Wait a minute. Yes. So I'm sharing your screen, team. So are you able to see the screen, team? This. So this is a solidly at the neutral 220 kV system, team. I am doing the lightning arrestor calculation for this. See, this is my system voltage, which is 245 kV. And the standard lightning impulse of my system is 950 kV, means all the equipments are having a BIL level of 950 kV. Now I am considering the earth fault factor K is equal 1.5 because as it is a solidly earthed system. And I am assuming the maximum duration of temporary load voltages is 10 seconds. And the nominal discharge current, I selected 10 kA and I selected class 3 lightning arrestor. And the maximum short circuit is 50 kA. Forget about this. Come to the minimum required continuous operating voltage and rated voltage. As I said, the minimum continuous operating voltage is 5% to the system voltage, which is 149 kV. And UR1 minimum is 1.25 into UC minimum, like 1.25 times of 149, it's coming to 187 kV. And again, one more method is there, as I discussed it, using the KTOV, this figure, come to this figure, this is the figure. For the 10 seconds, if you see the 10 seconds, what is the value? It's coming to here, 1.0 some kind, right? Let's go back to there. So it is coming to 1.4 into 1.4 is the safety margin into US by root 3. divided by that 1.075 what we have seen there. So that will results to 185 kVt. So what is the maximum in this? What is the maximum in this? Obviously this 187. So always 187 is the result. So mostly we won't do this calculation. We mostly rely on only this. So 187 is the this case. So again, obviously always remember the lightning arrestor rating should be divisible by 3T because each ZNO blocks is rated for 3 kilowatts. So it should be divisible by 3. So divide by 3, so 189 kV. Normally, a lightning arrestor with rated voltage of at least 198 kV is used in this system. Used in this system. For the 220 kV. For 220 kV, generally we will prefer 198 kV lightning arrestor. So even though for on these conditions, we got 189. But generally, 188 is the practically applied one. So 198 kV. So if I'm selecting 198 kV lightning arrestor, then again I am dividing it with 125. So I am saying that 150 kV is my continuous operating voltage of my 198 kV lightning arrestor. Now I am selecting the MO resistor team. So I am selecting this MO resistor suitable, which is with a 10 kilo amps and class 3. So as per the manufacturer, it was 60 mm dia MO. So with this factor, this is the like residual current, residual switching impulse residual voltage to the rated voltage. So with this diameter on using the energy capabilities, energy storage capabilities, this is the factor given by the manufacturer. So this is the 2.45. So it seems that 2.4 into the what is the rated current? 198. So 2.4 into 198 will gives you nearly 485. So the resulting protective characteristics is 485. Anyway, please remember the switching impulse protection level at for 1 kilo amp of the current. If 1 kilo amp of switching impulse means residual switching impulse with residual voltage applied, it is nearly equivalent to the 80 to 70 to 90% of the 75 to 90% of the 10 kilo amps lightning reduction impulse residual voltage, lightning current impulse residual voltage. So generally we will take 80% of this. So 485 into 80 coming to 420 kV. So it's not required much. So 485 is the main one we are checking the lightning impulse. Remaining all obviously will be much low only. So 485. So in the next step, we are checking the for actually my protection level of my switchgear is 950. But I am having I got my lightning arrestor is operating at 485 only. So what is the range of this? I mean the margin between the protective level to the rated equipment, which is 1.96. That should be obviously 1.4 as we discussed it. It is greater than that, so definitely sufficient for an application. And if you see the one more example here, before this is for 110 kV system. So at fault conditions, obviously it will change. So here it is 367 kV. So it is 1.5. So it is also generally sufficient. So we are checking the protective level of my lightning arrestor, and we are deriving this protective level, and also we are selecting this metal oxide by doing this by also we are calculating the continuous operating and rated voltages. So this is the way of doing. So for solidly earthed, let's see if my having the this is also solidly earthed 500 kV system. Yes, resonant earthed and this system. See, obviously at every case production level is 1.56. I have shared you this document to you, Tim. Yes, let's see the difference between the 20 kV solidly earthed lightning arrestor. Here I required 21 kV UR and 16.8 kV UC, and this is the class. This is the case. And if you see this for the resonant earthed system of 20 kV system, let's say 30 kV lightning arrestor is required.